This video is going to cover the elastic curve for slope and deflection. This is going to be using the double integration method, and the big thing that we need to focus on is boundary conditions and continuity conditions. So boundary conditions are when you're looking at supports effectively. So when we do double integration, we're going to have constants of integration, and these constants of integration need to be solved for. So if you're looking at a pin, what do you know is going to happen at a pin, or specifically at a roller at the end of a beam? You're going to say that there is no deflection, and there's also at the end no moment. Now, the no moment part doesn't really help us if we already know the moment equation in terms of x, but if we're going to be doing double integration from the load to get to the moment, then you'll need that to solve for constants of integration to get the moment equation, and then using double integration again, you're going to need to use our deflection part to get the constants of integration for slope and deflection. At a fixed end, you have no deflection and no slope. So this is what we're really looking for in terms of our boundary conditions. And again, this is a pin and a roller at the end of a member. If you have a pin or a roller that happens to be at the middle, then you don't necessarily know that the moment is equal to 0, but your deflection is still equal to 0. So for what we're concerned with, these are our boundary conditions that we're looking for with our supports. Now, when you have multiple different equations in terms of x, where those two meet, we're going to have continuity. So continuity is where one equation stops and the other equation starts. So usually when we're taking a cut on our beam, if there's a load here and we have a cut 1 and a cut 2, but both of our things are coming from the left side in terms of x here. When this is the case, obviously x is going to stop at the point of the load, and then it's going to start again with a different equation at part 2. And if both are coming from the same direction, if say x1 and we'll call it an x2 here, we'll say x1 is for cut 1, and then let's just say that there was, here's cut 2. If they're both coming from the same direction, then where x1 and x2 meet, that's going to be continuous, right? It should give you the same value for slope and deflection. So at this point, that means slope 1 should be equal to slope 2 at that part, and that part is right here, which does make sense. Obviously, your beam can't just have a certain deflection of like 2 inches, and then magically when you look at it from the other side, it's now 6 inches at the same point. That doesn't make for a continuous beam. And since we're measuring from the same direction, the same can be said about our slope. Our slope 1 is going to be equal to our slope 2 because we're measuring from the same direction. Now, if you were measuring from a different direction, if you're measuring for x2 here, you're measuring from the other direction, well, things are a little bit different. Still, when they meet at the same spot, when they're at the same spot, and that spot, we're not going to say that it's x1 and x2 are the same. Let's say that this is L, the length, and at this spot, we're going to call this a distance of, I'm going to call it A, just because I don't want to just use x here. And then the other direction is L minus A. So effectively, when x1 is equal to A and x2 is equal to L minus A, that's the same spot. So when they're at the same spot, then again, our deflection is going to be the same. However, due to our sign convention, that we didn't really talk about, but due to our sign convention, if you're coming from the left, deflection is positive when going up and theta is positive when going counterclockwise. However, if you're going from the right, if our x is going to be coming from the right here, going off to the left, deflection is still positive when going up, but this time theta is positive when going clockwise. So because of that, when those two meet at x1 equals a and x2 equals L minus a, theta 1 is going to be equal to negative theta 2 because the directions are going to be backwards. So that's what we're really looking for to be able to solve for our constants of integration. We're looking for our support conditions, and we're looking for where our equations meet together. So now let's solve a problem. So for this problem, it's going to be, I guess you could say, fairly simple. I mean, the setup's really simple. We're going to have a simply supported beam with a cantilever. So here I'll have a pin and we'll have a roller. We'll just kind of make it look a little bit better there. And we're going to have one load. This one load is going to be 10 kips along this beam, and it's 5 feet to the load, 5 feet from the load to the next support, and then we're going to say 7 feet over here on the side. So now that we have that, we need to talk about when to make cuts. Remember way back when we talked about moment equations in terms of x, you have to make a cut every time there's a change in load. And technically there's going to be a support reaction over here. You could call this AY. Now, technically, when solving for it, you're going to find that because this is mainly symmetric, if you just ignore the half, you're going to say that this is 5 kips, and that technically also this is 5 kips, because that 10 kips is centered. So if you were to sum the moments about this roller point, you would have this, I don't know if you want to call it AY times 10 minus 10 times 5, so therefore AY is then 5. And then you sum forces vertically, and you would get the other guy, if you wanted to call this BY, then you would get him as 5 as well. So now you see our loading situations, and now we have to make our cuts. So there's a change in loading here. We'll call this cut number 1. Then there's going to be a change in loading over here. This will be cut number 2. And then technically there is a change in loading over on this side, which is going to be number 3. So we need to make 3 cuts because there's 3 changes in loading. And that's going to be a lot of constants of integration that we need to solve for. So now we need to pick the directions that we're going to measure x from. So I'm going to say for the green one, we're going to measure x this way. For the pink one, we might as well, and we're going to stick with it. We're going to say x is this way. But for the purple one, let's take x off the side. So I'm going to call them x1, x2, and x3, just so that we can relate them with cut 1, cut 2, and cut 3. But technically, x1 and x2 are the same x. They're both measuring from the same direction. So in reality, you would actually call them both just x1. But I'm going to do it with colors, and I'm going to call them 1, 2, and 3 to relate to our different cuts here. So first up, we need to make cut number 1. So cut number 1, we're going to draw a nice pretty picture of our free body diagram here of cut number 1. And at cut number 1, we have literally our 5 kip load, and that is going across a grand total distance of, God only knows, x1 distance. That's what's happening. Now technically at these spots, we're going to have shears and moments, but nobody actually cares about the shear. We only actually care about the moment. So for the moment, all we have to do is sum the moments at the cut and set it equal to 0. So what we're going to get now is you have your 5 kip times distance of x, and then you have your moment. Those are going in opposite directions. So our 5 kip is going the wrong way, so we're going to have minus 5 times x and then plus m. So ta-da, m is equal to 5x. Now that we have our moment equation, what we need to do now is solve for our slope and deflection. And remember that slope times the flexural rigidity is equal to the integral of the moment equation in terms of x times dx. So again, that's going to be the integral of 5x dx. And when you take an integral, it's going to be 5 divided by 2x squared plus the constant of integration. Yes, that's what we need to solve for. So that is, of course, theta EI. I'm going to call it theta 1 because this is our cut 1. Then if you actually want to solve for deflection, again, I'll call it deflection 1, it's times the flexural rigidity. The deflection times the flexural rigidity is equal to the integral of the slope equation in terms of x dx. So for us, that's going to be the integral of 5 divided by 2x squared plus c1. Okay, so now we're going to take this lovely integral over here, and for our deflection equation times the flexural rigidity, we're going to get minus 5 divided by 6x cubed plus 25x, doing the wrong one here. We're going to get minus 5 divided by 6x cubed plus c1x plus c2. Not even minus, it's plus. Wow, totally messed that one up when I was reading. Anyway, there we go. Now we have deflection, now we have slope. So 5 divided by 6x cubed plus c1x plus c2. We're going to do the same thing when we go to the next cut. And I'm just going to kind of skip through this because I don't think anybody really needs to watch me calculate moments again and again and again. So over here, we're going to do cut number 2. So cut 2, and what cut 2 looks like, just to remind everybody, cut 2 here. Same 5 kip load, right? Same 5 kip support load. And this time we have our 10 kip force, and that's 5 feet away, but technically across the bottom is all x. Again, we have shear and we have moment. So when you solve for that moment equation is going to be minus 5x plus 50. Okay, cool. So now when we're going to take our integrals, we're going to get that this is going to be theta 2 times EI. Again, it's the integral of the moment equation, so take the integral of our minus 5x plus 50 here. And what we're going to get for this one is minus 5 divided by 2x squared plus 50x plus, it's not C1, it's not C2, we already have those. This will be C3. All the C's here. Again, do the same thing. We're going to get deflection 2 times flexural rigidity. This is where I was getting the minus 5 divided by 6x cubed plus the 25x squared now, plus C3x plus C4. So again, nice, lovely equations. Now for cut number 3 is going to be just ever so slightly different. So for cut number 3 here, my beam looks like this. The distance is x, and this time my cut's on the other side, so I have shear up moment this way. So the moment equation, in terms of x, there is no moment. Isn't that great? You're like, ooh, so then there's no slope? No, there's still slope, right? Because when you integrate 0, when you integrate a constant, that's when you're going to get, when you integrate a constant value, then you're going to get something in terms of x, right? So if you have 0, then you had a constant when you took a derivative. So there is still going to be a c. So this one, slope 3 EI, when you take the integral of 0, technically, you're going to get a constant value. So that's going to be C5. Yeah, not a very glamorous equation, that one. And same thing when you do the deflection times the flexural rigidity and you take the integral. Obviously, then you're going to get C5x plus C6. So ta-da. So they're not really glamorous equations, but they are still there. They still do matter. So now that we have all these things in terms of C1, C2, C3, C4, C5, and C6, now we actually have to solve for our constants. So how do we solve for our constants? Well, again, we need to look for boundary conditions. So our boundary conditions, we're looking for times where there's really supports, right? And we have 2 supports. We have this pin and this roller. So remembering the cuts that we have here, for cut 1, I'll write it in green. For cut 1, we go from 0 to x all the way until 5 feet, where that 10 kips is. For cut number 2, we start at 5 feet, then we go to wherever x goes all the way to 10 feet, where that roller is. For cut number 3, though, we're going the other way. We're going to start from our other 0 and go all the way to 7 feet. Okay, so x1, if we were to color it in here with green, x1 only goes this far. x2 technically, I guess we'll do it in this kind of pinky color. x2 technically is the equation for this part, and x3 being in the purple, x3 is this part over here. So you see we do have our 3 equations. So at our supports, we're seeing, okay, so the pin over there is going to be where support number 1 is in cut number 1. So that's at x is equal to 0, correct? So at x equals 0, we're looking in our green one because that's in our green section. And what happens there is that our deflection, right, is equal to 0. Because it's at a pin and it can't deflect anywhere, the pin's holding it in place. So I'm going to plug in 0 times EI technically is equal to, we have 5 divided by 6 times x, who is 0 cubed, plus C1 times x, who we just said was 0, plus C2. So, ta-da, we get C2 is equal to 0. That is so wonderful. It is so wonderful to start off with a 0 for one of your constants. That makes everything actually just beautiful. The next one that we have, though, we're going to have another one. It's going to be in the cut 2 region, correct? Or the cut 3 region. We're going to have both, right? We have the roller. So the roller is at, we have at x is equal to 10 feet, but technically it's x2, right? Because we're in the x2 equation here. So when x2 here is equal to 10 feet, that's us being right here, then we have deflection is equal to 0. So again, we're going to look at our x2 equation, which is right here, and we're going to plug in 10 for x and 0 for our deflection. So technically 0 times EI is equal to minus 5 divided by 6 times 10 cubed plus 25 times 10 squared plus C3 times 10 plus C4. Okay, well, as you can see, you ain't really going to solve for anything there. So I'm going to just call this equation 1 because we didn't really solve for it. So what's actually going to happen with these boundary conditions is when we're plugging them in, we're going to get a whole bunch of equations, and these different equations we're going to have to solve simultaneously. So it's kind of fun in a wonderful sense, isn't it? So any other boundary conditions? Technically, we also have that when x3 is equal to 7, if we go the other way, when x3 is equal to 7, that's also there at that roller. So at x3 was equal to 7 feet, we also have our deflection is equal to 0, but it is the deflection 3 equation. So that's C5x plus C6. So we're going to have 0 times EI is equal to, we said it was C5 times x is 7, plus C6. Okay, again, we didn't actually solve for anything, so I'm going to just call this equation 2. Right, nice and lovely. So you can see we had 3 boundary conditions. We solved for 1 constant so far and nothing else. So now we need to go and talk out of 6 constants. We only actually have 1 of them. So now we need our continuity conditions. So again, this is where the 2 equations meet. So for instance, obviously, at this point right here, we have the difference, so the starting and ending point of our 2 equations. So x1 and x2, and remember they are measuring from the same side. So when they measure from the same side, we're going to have same deflection and same slope. So again, we have over here, we're going to have x1. And so when x1 is equal to 5 feet, and our x2 is also equal to 5 feet, right? Because one ends, one starts. At that point, we're going to have that our deflection 1 is equal to our deflection 2. Okay, so we're going to plug those in. So deflection 1, our deflection 1 equation, here it is. And our deflection 2 equation, here it is. So we're going to plug in 5 for x on both sides, and let's see what we get. So here we go. We're going to have, here's deflection equation number 1. So we're going to have 5, I actually need to be marking up in a pen here, 5 divided by 6 times x, which is 5 cubed, plus c1 times x, plus c2, but c2 was 0. Great. That was actually deflection 1. And this is going to equal our deflection 2 equation. So minus 5 divided by 6 times x, which was 5 cubed, plus 25 times x squared, plus c3 times x, plus c4. I got a C1, a C3, and a C4 all in this stuff. So if I actually were to simplify this down, I'm going to get 0 is equal to 416.7, it's like 0.666 repeating, plus 5C3 plus C4 minus 5C1. I'm going to call this equation 3. Didn't really help much, right? So equation 1, I've got C3, I've got C4. Equation 2, I've got 5 and 6. And equation 3, I've got 3, 4, and 1. Woo! Okay, what else do I have going on? Well, we also said that when our x1 is equal to 5 feet, and we also had our x2 here, who is also equal to 5 feet, because they're going from the same direction here, I'm also saying that slope 1 is equal to slope 2. Okay, so let's look at those equations, slope 1 and slope 2. Okay, so slope 1, nice, and slope 2, a little bit longer. But notice that there's only a C1 and a C3. That could help, that could help. So down here, we're going to have, plugging in 5 for x, for theta 1, slope 1, we're going to have 5 divided by 2 times x, which is 5 squared, plus c1, that's slope 1, is equal to, same slope because same direction for x here, minus 5 divided by 2 times x squared, plus 50 times x plus c3. So what I'm going to get now is I'm going to have an equation for C1, which is equal to 125 plus C3. So you're thinking, oh my God, here's equation 4. But actually, I have a C1 in terms of C3. And if I go and I plug this back into here, I'm going to have an equation that's going to be in terms of C3 and C4. And you know what? I already have an equation up here in terms of C3 and C4. So let's do that. Then I will be able to solve for my C3 and C4. So when I plug that in up there, I'm going to get 0 is equal to 416.7 plus 5C3 plus C4 minus 5 times 125 plus C3. So actually, I have 5C3 here, and I'm about to minus 5C3. C3 goes away. That's actually kind of cool. So now I'm actually going to get that C4 is equal to 208.3. Okay, nice. But that was C4. Funny enough, that wasn't even C3. However, now that I have C4, remember we just talked about way up here at equation 1, I just have something in terms of C3 and C4. So now that I have that, let's go plug C4 into my equation 1 here. And let's see what we get. So into my equation 1, which I didn't actually simplify it down, but my equation 1 actually simplifies down to 166.7 plus 10C3 plus C4 is equal to 0. That's the actual simplified down equation. So when I plug C4 up into that, I'm going to have 166.7 plus 10C3 plus our C4, who's 208.3, is equal to 0. So lo and behold, I'm going to get my C3 value, or C4 value. So here we go. We're going to get C3. I already have C4. So C3 is equal to minus 37.5. Okay, cool. And then literally you can see it right here. If I plug in C3 there, I'm going to get C1. So my C1 value is then 125 minus 37.5. So I should write that down, minus 37.5. We're going to get 87.5 for C1. So, okay, cool. So I got 1, 2 is already 0. I got 3, and I got 4. I don't have 5 and 6, though, and I do have an equation for that. So, okay, we're not quite done yet with continuity. What other continuity condition do I have? Well, this time I'm going to look at x2's coming this way and x3's coming this way. So they're going to meet in the middle there. So now I have when x2 is equal to 10 and x3 is equal to 7, because they're in opposite directions, my slopes are going to be opposite. So at x2 is equal to 10 feet and x3 is equal to 7 feet, my theta 2 is going to be minus my theta 3. Okay, so let's write out theta 2, our slope 2 here. So slope 2, again, is minus 5 divided by 2 times x squared, x being 10 squared, plus 50 times x is 10. And then what constant did we have there off into slope 2? C3. So C3 we just found is minus 37.5. Okay, cool. That is theta 1 and theta 3. We need negative theta 3. So negative slope 3 is just C5. Yeah, just C5. That's kind of cool. But remember, it's minus. So he is equal to minus C5. That's just a whole bunch of numbers. So congratulations. We're going to actually get that C5 is equal to minus 212.5. Wee, that's nice. And again, we said way back up here, we actually do have an equation with C5 and C6. So yay, let's plug that back up into number 2. And we're going to get, it is actually 7 times C5, which is minus 212.5. And we said plus C6, and all that equals 0. So wow, lo and behold, C6 is equal to a really big number, 1487.5. Cool, so we did it. We found every single constant of integration. Not very fun, but we did it. So now all we have to do is actually write out our equations. So for our first one, we go from 0 to x, technically our x1, to 5 feet here. And we said our slope 1 equation times EI is equal to, we had 5 divided by 2, x squared, plus C1. We said C1 was 87.5. Technically, because we integrate, a moment is in kip inches, but when you integrate in terms of length, the length's going to get one more factor to him. So we have kip inches squared. Then we have our deflection 1 times EI, our flexural rigidity, and we're going to get 5 divided by 6 times x cubed plus 87.5x plus C2. C2 is 0. Again, when you integrate in terms of x being the length, you're going to get kip inches cubed. You might be thinking, that is definitely not what I would consider to be the units for deflection. You are correct. However, remember that this is times EI. EI being modulus of rigidity and the modulus of elasticity and the moment of inertia, which becomes the flexural rigidity. So yes, when you actually divide then by EI, then you actually just get inches. So do pay attention to your units. Then we have our next one. So for 0 goes to, this is the same x, right? It's the same x direction, but we called it x2 for the cut. My bad, it's not 0. It's from 5 feet all the way to 10 feet. Same x though, same x. Our slope 2 equation times EI is going to be equal to minus 5 divided by 2x squared plus 50x. This was C3. C3 we had as minus 37.5. Again, kip inches squared. Then for deflection 2 times EI, we're going to have minus 5 divided by 6x cubed plus 25x squared minus 37.5x plus C4. C4 we had as a big whopping plus 208.3, and this is now in kip inches cubed. Cool. Then lastly, for our new x, this x goes from 0 to x3 to 7 feet. He's going the opposite direction than the other two of them. And his slope 3 times EI is equal to just C5. And C5 we just said was minus 212.5. Again, that's in kip inches squared. Then for deflection 3 times EI, we get C5, which was minus 212.5 times x, plus C6. C6 was 1487.5 kip inches cubed. So in terms of answers, there we have our slopes and deflections at every single point. So doing the math again, it's literally just calculus. It's not that bad, and solving for constants of integration really isn't that bad. The only thing that's kind of tricky is making sure you're watching your boundary conditions and your continuity conditions. And yeah, it can suck a little bit to actually solve for these, but really the biggest thing you have to watch out for is making sure that your moment equation in terms of x is correct. You could be solving for your constants, you could be doing an integration correctly, but if you can't actually calculate the moment equation in terms of x, then it's kind of all downhill from there. So they're long problems, but they're not exactly too difficult to actually solve.